welcome back. In today's class, we will be discussing about partial differential equations or PDEs, PDE for partial differential equation, and in particular we will be discussing the so called finite difference method. In the last class, you have already solved a second order differential equation which was something like d2y dx2 plus something into dy dx and so on so forth, and there the finite difference method was already introduced where you solved y versus x. So, that was basically a differential equation and that was only a one variable problem. Whereas, in partial differential equation, as you might know, you essentially have a quantity, suppose temperature or displacement as a function of x and y, a multivariable. Basically, it is a differential equation in multivariable in multiple variables, and you have to solve those. Right. Now, in your physics course, you must have come across various partial differential equation, the most common being the so called wave equation, which is basically a double derivative of u in time. U might be a displacement, it might be a density, location of the density peak and so on and so forth, and that is related to c square, where c is the speed of the wave into grad square u, right. And grad square has been written as the Laplacian or like the divergence of a gradient operator, and in more simpler cases you might have come across the wave equation as del 2 u del y 2 equal to c square del 2 u del x 2, but this gradient, this d2 dx 2 in general in 3 dimensions can be written as grad square, right. And other than the wave equation, you must have come across the so called Laplace's equation in electrostatics, grad square phi equal to 0, where phi is the electrostatic potential, and this equation is valid when there is no charge in the place where you are calculating phi. In more general, in electrostatics, you would have come across the so called Poisson's equation, which is grad square phi, phi again being the electrostatic potential equal to rho x y z, the charge density as a function of x y z, and you can solve this equation to at the points where there is a charge density to calculate the electrostatic potential. Maxwell's equations of electromagnetic theory are written as partial differential equation, divergence E equal to rho, is rather rho by epsilon, and basically divergence B equal to 0, curl of E equal to minus del B del T, and curl of B equal to mu 0 j, j being the vector, the current vector, plus mu 0 epsilon into del E del T. So, these are all examples of partial differential equations. Moreover, you might have come across in your statistical physics course about the so called diffusion equation, and that relates the single derivative with respect to time. So, suppose n is a quantity, n could be suppose the density, number density of molecules in a certain volume, and del n del t equal to d, d being the diffusion constant into grad square n, right. So, in contrast with the wave equation, you have a double derivative with respect to time here, here you have a single derivative with respect to time. Okay. So, in the next rest of the class we will be solving the diffusion equations under different conditions. So, let us discuss the diffusion equation in a bit more detail. This is of course a partial differential equation, and let us suppose that n, right, is the number density of particles over space. So, suppose this is some box or a channel, and here you have higher density of molecules which is suspended in water, say, and here you have a lower density. Now, you might have read about Brownian motion, and what you expect is that these particles from the higher density regions are going to diffuse slowly and come towards the lower density part, right. So, n is the local number density of particles, and if you plot n versus x, x being this direction suppose, right, then n is increasing as a function of x. So, this is the n at high density region, this is n which is a function of the number density is a function of x, y and t. So, n x y t, this is the low density region, and to get where the diffusion equation comes from, one can understand it as the so called Fick's law. Okay. So, what does the Fick's law state? Fick's law states that the particle current, what is the particle current? Particle current J is the number of particles crossing per unit area per unit time, right. So, the number of particles moving in this direction, say per unit area per unit time, that is the particle current, and that as per Fick's law can be written as minus d, d being a proportionality constant, grad of n, n being the number density. So, it is basically saying the current is proportional to how fast n, the number density, is changing as a function of x. Why is this minus sign here? Why is this minus sign? So, the current, the particle current will move in this direction, right. So, it is in move, the particle current will move in the negative direction, but n is increasing in the positive direction, right. So, hence the particle current is opposite to the direction of gradient of n, and which is the Fick's law. And in addition, the conservation of mass is typically written in physics as such a in such an equation, del n del t, and again reminding you is the number density of particles. So, in a certain volume, how fast is the number density changing, and that is proportional to the flow of particles, the particle current which is entering the certain volume. So, this is nothing but the so called differential form of the Gauss's law, which you would have studied in your BSc, right, and this is how you write your conservation of mass, and combining the Fick's law with the conservation of mass. So, basically del n del t minus divergence j, instead of j you use the Fick's law, you just substitute minus d grad n, and what you get is d grad square n x y z t. And if you solve this partial differential equation for the appropriate boundary conditions, you shall know how does n change as a function of time with time and as a function of x y z. So, this is the differential equation, and a partial differential equation if it is in x y z multivariables, if basically density is changing in the x direction as well as in the y direction, there is a certain current, etc. If you solve it, you will get the so called solution to the diffusion equation. Where else have you seen the diffusion equation? So, basically now if you talk about heat conduction through a metallic plate, right. Now, this is again a problem which you would have studied in class. Now, suppose this is a metallic plate, and at one end you fix the temperature at T2, at the other end you fix the temperature at T1, at t equal to 0, at time t equal to 0, and you want to find out what is the temperature distribution within the metallic plate. Now, if the plate was at a temperature, different temperature T0, and you put them between two regions at temperatures T2 and T1, then the temperature of the plate itself shall evolve in time, but after it reaches steady state, after a considerable period of time, the temperature variation along the plate, on the plate, will be basically independent of time, and t will be a function only of x and y. Okay. So, to study the problem, what one uses is the so called Fourier's law, and this is very similar to Fick's law. And there what you say in the Fourier's law is that the heat current. So, in the Fick's law you had the particle current, and here you have the so called heat current, which is a function of x, y and t, is proportional. So, this is the so called proportionality constant, the thermal conductivity, right, and the heat current is proportional to the gradient of temperature. So, that is what the Fourier's law is. So, what you did in the Fick's law was del n del t, the particle current was proportional to gradient of the number density. Here in this case the heat current is proportional to the gradient of temperature, right. And just to remind you, I have written down that q x y t, the so called heat current, is nothing but the magnitude of heat flow at point x and y at time t per unit area. That is the heat current, how much heat is passing through a unit area, right, at time t, and that is a function of x, y and t. Kappa is the thermal conductivity. What is thermal conductivity? It is the amount of heat, that passes through a unit area per unit time when dt dx equal to 1. So, that is the heat current, and just like the conservation of mass, you can also write the conservation of energy in a unit volume, right. And del q del t, q is capital here. So, here q is capital here, right, and q is the internal heat energy per unit volume. So, how much heat energy per unit volume is increasing in a certain time, the rate of change of heat energy per unit volume, and that is proportional to the gradient in the heat current, or sorry, the divergence of the heat current, right. It was very similar to this divergence of current, and again here you have divergence of current, being heat current being denoted by small q, and the total amount of heat in a certain volume is a scalar quantity being represented by capital Q, right. And this small q, the heat current, by the Fourier's law can be written like this: minus divergence of minus kappa, kappa being the thermal conductivity, into gradient of temperature. Temperature is a function of x by t, and that in turn can be written as kappa into grad square t, right. Now, to put it in the diffusion equation form, I would ask you to remind yourself that del q del t is this quantity del q del t, the amount of heat per unit volume, the amount of heat change per unit volume, the rate of change of it, it's because it's a derivative with respect to time, is the specific heat capacity C into the density into dt. So, this T, the T at the numerator, capital T being the temperature and the small t being the time, right. So, as the temperature increases, if the temperature increases fast, quickly, then the energy in that volume also increases quickly, and that is related to the specific heat capacity C and the rho, rho being the density of the material, right. So, just to remind you, what is C, specific heat capacity? C is the amount of heat in joules to raise the temperature of 1 gram of material by 1 Kelvin, right. And so, C rho is essentially the amount of heat required to raise the temperature of a unit volume, right. We are talking Q is per unit volume. So, the amount of heat required to raise the temperature of unit volume of material by 1 Kelvin, and this relationship holds if you just look up your whatever BSc physics course, and this. So, del q del t equal to this quantity we are going to basically substitute here, right, and that is exactly what I have done here, and then you get C rho del t, capital T by del t time equal to kappa grad square T, and this is nothing but the diffusion equation again, right, where I am writing kappa by C rho as kappa dash, right. And this is very similar to the diffusion equation you saw just here, right. So, this is absolutely similar. Now, as I said before, when the system reaches steady state, right, steady state, suppose this is your material and you are holding one edge of the material at temperature T2, the other edge is being held at temperature T1, right. Then you can solve the diffusion, then you can solve the so called diffusion equation, and once it reaches steady state, there will be no explicit time dependence in the temperature. If T will be a function of only x and y, which means that the temperature is not going to change as a function of time. So, del T can be written equal to 0, which means grad square T equal to 0, which is nothing but the Laplace's equation, which you also solve for electrostatics. Just to remind you, steady state is not equilibrium, because in equilibrium you would have the temperature uniform over the entire space. Steady state means that there will be a current, there will be a heat current, a certain amount of heat is going to enter this end, and in steady state an equal amount of heat is going to leave this surface. From the other end, there will be a temperature profile, there will be a T as a function of x and y, but that is not going to change. In steady state, there will be a net heat current, and what would be the what would be the temperature profile across in this region? We can find it out by solving the so called grad square T Laplace's equation when appropriate boundary conditions are given. Right. Now, you might have handled such problems in one dimensions in your college, in your BSc or your masters, considering that y and z being infinite plates, being infinite in this direction, and this, and suppose this is the x direction, and you find out how the temperature varies around along x. But suppose instead of considering a fully blown T as a function of x and y and z, suppose along z there is no temperature difference. So, T does not vary along z, but it varies along x and y only, right. Suppose T varies along x and y only, and you have finite boundary. So, this is of a finite dimension and not extending along y, and the question is to solve the temperature profile, one has to solve the Laplace's equation and given the appropriate boundary conditions. Okay. So, what is the Laplace's equation? It is nothing but grad square phi equal to 0, or in this particular case basically grad square T as a function of x y equal to 0. And if there are no explicit z dependence, let us solve the Laplace's equation, that is the case where T is a function of only x and y. Then we can write this as del 2 T temperature del x 2 plus del 2 T del y 2, right, equal to 0. And just to remind you from the last class, by the finite difference formula, one can write del 2 T del x 2 as T at x plus delta x plus T at x minus delta x minus 2 T calculated at x divided by delta x square. So, what are we doing? We are basically discretizing space. So, suppose your space started here at x equal to 0 and it the metal plate ended at Lx, right. So, what we are going to do is calculate the temperature at discrete points within this range, right. So, if you have continuum, you have infinite points between 0 and Lx. Instead, on the computer we are going to calculate temperature at discrete points between 0 and Lx. So, suppose call the one end of the plate, which is 0, basically the first point, and the neighboring point to be the second point, and then the third point, fourth point, and so on, the I minus 1th point, ith point, and I plus 1th point. And the distance between, say, the third point and the fourth point is delta x, right. So, you are calculating temperature at discrete points of space separated by delta x, and the distance between 1 and 2 is delta x, and then basically this is how you can write down the second derivative, right. Basically, you are calculating the temperature at suppose x plus delta x, like I plus 1. This is would be the temperature at T minus delta x, and this is the temperature at x, right. And just to remind you that the first derivative del T del x can be written as T temperature at x plus delta x minus temperature at x minus delta x by 2 delta x. And how these formulas come? You can look up the book, and there are Taylor's series expansions, and then there are first order expressions and second order expressions. Those are important, but not possible to cover in this short class. So, if you are interested, and you should be, please look it up. Okay. So, this was the expression when you had del 2 t del x 2. Now, when we are writing a partial differential equation, right, then this expression will become this is this expression, and correspondingly you will have del 2 t del y 2, and that is basically this expression, right. So, it is very similar, except now the derivative, the y plus delta y is taken, x is remaining constant, this x y remains again, x is unchanged, and here again you are taking y minus delta y instead of x minus delta x, y minus delta y, x plus delta x, x remains the same, y plus delta y, because now you are taking the derivative in the y direction, right. Previously, you were taking derivative in the x direction, now you are taking derivative along the y direction, say, right. Now, if that entire space, so from here this was in one dimension. If you think about two dimensions, what you have is basically you have discretized space in the x direction separated by delta x, and in the y direction you have again separated, you have discrete points in the y direction separated by delta y, right. And now you can calculate basically these quantities x plus delta x y and x minus delta x y. You can write them in terms of I and j, where I and j are discrete, they have numbers like 1, 2, 3, 4, so on so forth, and each of these points, suppose this is I on j, the point x minus delta x would be this point, right, separated by minus delta x. Similarly, y plus delta y will be basically this point, right, this discrete points I and j plus 1, the neighbor in the y direction separated by delta y. So, this term can be written like this, where x plus delta x has been written as I plus 1, y remains fixed, j remains fixed, and here again x y corresponds to I j, x minus delta x, there is an error here. So, this is T I minus 1 j, right, and similarly this should be j minus 1. So, corresponding to minus delta x you have I minus 1, and here where you have y plus delta y and y minus delta y, you have basically j plus 1 and j minus 1, right. So, basically when you discretize space, this minus delta x you are writing in terms of lattice points. So, basically this is your expression of the Laplacian when you have discretized it and use the finite difference expressions for it, and your aim is basically if you know all these different terms, you have to find out T I j. So, T I j, the temperature at a certain point I and j can be written as, I have just basically played around algebraically with this equation, and this can be written as T I j can be written as delta x whole square into delta y whole square upon 2 delta x whole square plus delta y whole square. Please work it out, you will see that it will come, and what remains within the brackets is T I plus 1 j, T I minus 1 j delta x whole square, then T I j plus 1 plus T I j minus 1, and in the denominator you have delta y whole square. Now, if delta y is chosen to be delta x, so that you essentially have a square lattice, right, then this expression becomes even simpler. Basically all these terms cancel out, just put delta x equal to delta y and the expression becomes so simple, right. The one within the bracket remains the same, but this becomes just 1/4. But to solve this partial differential equation, you need the so called also the boundary conditions, right. And basically in the boundary conditions, now when you used to solve this in suppose 1D, right, you would have solved this. So, then just to remind you, and I will remind you that, and then in turn tell you that when you are solving this problem in 2 dimensions, when you have del 2 t del x 2 plus del 2 t del y 2, how the boundary conditions are going to change. Just to remind you, when you were doing it in 1 dimension, grad square t equal to 0 would be nothing but del 2 t del x 2 equal to 0, right. There was no y dependence, and then you can solve this del t del x equal to C 1 and t equal to C 1 x plus C 2, and the boundary conditions would be that the temperature is T 2 at x equal to 0 and temperature is T 1 at x equal to L x, and then you just substitute and you would get a straight line variation of the temperature from T 2 to T 1 along x. But that can be done analytically, but now if you have more complicated temperature variations, right. Now, suppose this is your box, this is your metal plate, you are specifying the temperature on this, on the boundaries, which is basically along this and along this and along this and along this, these are the boundaries, right. So, you have to specify the temperature, and to take a slightly non-trivial problem, suppose the temperature was not fixed T 2 on at x equal to 0, which is on this plate, but the temperature was 0 at this point, the origin, basically the 1 point, but temperature was gradually increasing from point 1 and point 2 and point 3 as you move, suppose j equal from 1, 2, 3, 4 up till the end. Now, suppose you are taking a 34 cross 34 lattice, right. So, the temperature would increase from 0, 0.1, so on so forth to 3.3, and suppose along the x direction, here the temperature from here, which was 3.3, would decrease 3.2, 3.1 and so on so forth up till temperature 0 at L x and L y at this edge, right. And similarly, on this edge along x, here again temperature gradually increased from 0.1, 0.2, 0.3, so on so forth to suppose 3.3, and along this temperature is decreasing from 3.3, from 3.3, 3.2, 3.1 and so on so forth to 0. So, we have complicated this situation, right. So, now suppose the boundary conditions are such, the temperature are such that temperature is again increasing along x in this direction, but temperature is decreasing here at x equal to L x along y. So, that this point is again 0, same as here, and again along this temperature is decreasing. So, these are the boundary conditions. The temperatures along the boundaries are fixed, you cannot change them. They are conditions, externally given boundary conditions, and what you have to do by solving the Laplacian is find out the temperatures at these middle at these points within the metal plate as a function of x and y or I and j as you would like, right. The boundary conditions are given. You have this expression T I j. If you know the temperature of the neighbors, then you can find out the temperature at any point, and at the iteration number, note I am not using the word time, iteration number 0, you can set the temperature, the unknown temperature here inside to be say 1 or 0, it does not really matter. But because you do not know, you have to iteratively find out the right temperature, you have to find out the temperature distribution as a function of x and y, and all that you know is the temperature at the boundaries of the box. And if you know the temperature at the boundaries of the box, then you can find out the temperature iteratively here. Here the temperature might be 0 in the first iteration, here you have a finite value of the temperature, thereby you find out what the temperature here is, and if you know the temperature here, then this is again 0 and you can find out in the next iteration what is the temperature here. So, in each iteration you try to find out the temperature of all the points, leaving out the boundaries because the boundary temperatures are fixed. All that is evolving because of the boundary conditions are the temperature within this square plate, the points within this plate, not at the boundaries, and you find out the temperatures with each iteration at each of these points. And just like in the previous class, when you see that from one iteration to other iteration, the temperature at any point within the square boundaries does not change less or changes less than a certain tolerance level that you fix, it might be 10 to the minus 4 say, right. Then you say okay, this is my final temperature distribution, this is how my temperature is going to be distributed in x and y, right. So, what we are going to do today is very similar to what we did in the previous class, where we had only a differential equation. Now, we are just solving it in 2 dimensions, right, using this formula. Moreover, there the boundary conditions was only at x equal to 0 and x equal to 1. Here we are specifying the boundary conditions not at 2 points, but along 4 lines. These are the 4 boundaries, and we are specifying the boundaries, what the temperature is at each of these points along the boundaries, right. With that, let us move to the computer. The basic principle is the same. We are going to have an endless do loop, and only when the temperature variation from one iteration to the other at each of the points does not change or changes by an amount lower than the tolerance, we say okay, we have iteratively reached our temperature profile. So, now let us move to the computer and see how the thing works. Okay.